Okay, so a couple days ago, you guys read in the book about a town, um, Riverwood, that has a river called the Snake River. And all of a sudden, one day, the townspeople noticed that all the fish had died in that river. And they're trying to figure out what possibly could have killed the fish. And we know from our solubility lab that a lot of things can actually dissolve in water. So is it possible that something dissolved into the water in the river and caused all these fish to pop up dead? That's something that we're definitely going to want to look into. But we need to know about how these things actually dissolve into the water, what's happening with the molecules, what are some of the rules that they follow, in order to understand if this is possible to be the reason as of the fish being dead. Okay. So one thing that we learned about is that water is a polar molecule, okay, meaning one end of the molecule is negative and one end is positive. We also know that polar molecules are attracted to each other because you have a negative and a positive. It acts like a little magnet, and magnets are attracted to each other. Not only are the water molecules attracted to each other, but if you get an ionic compound in there, an ionic compound is a compound that has one positive piece to it and one negative piece to it, kind of like the water molecule, although a little bit different. Well, you just pretty much are putting water magnets by ionic magnets. So if you can see here, the negative end of this water molecule is attracted to the positive part of that molecule, and that's true of all three of these. The negative parts are coming in and attaching to that positive piece. On this side, it's reversed. The positive end of the water molecule is being attracted to the negative end of that molecule. Well, what happens then is you get these attracted to each other, and these water molecules are actually going to grab on. These ones will grab onto the Cl. These three will grab onto that Na, and they're going to pull those two apart. Okay? Because these attractions exist, that is why we can dissolve things. When the Na and the Cl, NaCl is salt, table salt. When that Na gets pulled away from the Cl by those water molecules, that is exactly what dissolving is. I'm going to show you a quick video here so that you can kind of see it in action.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions.
So those water molecules are just
The entire crystal
piece by piece
to solution.
pulling apart the salt. And that pulling apart is actually dissolving. Okay. Oops. All right. So as you pull those pieces apart, that salt dissolves, and you can see how those little water molecules come in and they just pull apart all of the salt. So something else that we learned is that like dissolves like. You can see that that's a rule that we're going to follow, and this is a rule that we covered when we did our solubility lab. So if you have a polar molecule, that's going to dissolve in a polar liquid. If you have a nonpolar molecule, that's going to dissolve in a nonpolar liquid. So like dissolves like, polar dissolves polar, nonpolar dissolves nonpolar. So that's why salt, which is polar, dissolves in water, which is also polar, and those opposite poles come and pull each other apart. All right. And if you try to put salt, which is polar, into oil, which is nonpolar, the salt will not dissolve. All right, because those are not like and like. Like dissolves like, polar dissolves polar, nonpolar dissolves nonpolar. And that rule holds true all the time. Okay. Here's a picture of a polar molecule. Remember, polar just means you have a positive end of the molecule and a negative end. And something that's nonpolar is either going to have no charges at all or charges that aren't evenly spread across the molecule. Okay, so here this acts like it has like a magnet, a negative pull on the magnet and a positive pull on the magnet. So it can pull things apart. It also is going to be attracted to other magnets. Here there's no attraction between molecules. So here's a question that I sort of already answered. It says, why does sugar dissolve in water but not in cooking oil? Okay, so I was talking about salt. This time we're talking about sugar. So if sugar dissolves in water, we know that water is polar, right? So that means sugar, because it dissolves in water, must also be polar. And if sugar does not dissolve in cooking oil, then we know that cooking oil must be nonpolar. So because sugar and water are both polar, sugar will dissolve in water. But because sugar is polar and cooking oil is nonpolar, sugar will not dissolve in cooking oil. Okay, here's another question for you. And this is just looking at about how much of something we can dissolve. There is a limit to it, right? Like when you were little and you wanted to make Kool-Aid and you wanted to make the sweetest Kool-Aid you possibly could. So it said to put 5 cups of sugar, but you just kept going. You wanted to put as much sugar as you could in that Kool-Aid. Well, eventually, pretty soon you keep adding sugar and it stops dissolving. It just sits in the bottom of your Kool-Aid jar. Well, that's because you can only put so much of a solute or a solid into that liquid. So just thinking about it, do you think that more sugar would dissolve in 1 liter of water or 2? Well, hopefully you think that you'd be able to dissolve more sugar in 2 liters of water. And actually, you should be able to dissolve twice as much in 2 liters of water as in 1, because each liter of water can hold a specific amount of sugar, and then it's what it's called full or saturated. Okay. Another question to think about is, would you be able to dissolve more sugar in cold water or hot water? And the answer there is hot water. The reason you can dissolve more in hot water is those hot water molecules are moving faster, so they'll be able to pull that sugar apart more effectively. Okay, so we have these graphs, which you'll become very familiar with, and you have this in your notes as well. This is called a solubility curve. And basically what this curve shows is how much solute or how much solid you can dissolve in a given amount of water. So everything on this graph is for 100 grams of water. So you imagine you have a beaker with 100 grams of water and you want to know how much KNO3 you can dissolve in there. Well, that's going to depend on temperature, because like we just said, the warmer that you get that water, the more solute or solid you'll be able to dissolve in there. But the trend is clear here. So as you warm something up, you're able to, if we just look at this red line, you're able to dissolve more solute in there. So the way that you would read this graph, okay, you know, at 20 degrees, if you go up to that red line, you can dissolve about 30 grams of KNO3 if the water is 20 degrees and it's 100 grams of water. Okay, if you heat that water up to 40 degrees, you can now dissolve 60 grams in that 160 grams of KNO3 in that water. Okay, and as you heat it up, you can dissolve more and more and more. Now, each different solute will have a little bit different curve. So this only applies to the chemical KNO3. If you want to know about NaCl, you have a different line you're going to look at. And if you want to look at KCl, here's another line you can look at. Okay, so if I said how many grams of KCl would be dissolved if the water is 80 degrees, you look over here for 80 degrees, go up to that line where it's KCl, take a turn, 50 grams will be dissolved at 80 degrees. Okay. If this is confusing you, now is a really good time to pause the video, raise your hand, and ask for some clarification. Okay. Here's some more sort of example questions that we can work through. So very similar to what you see on your quiz or your tests that'll be coming up. how much potassium nitrate will dissolve at 60 degrees Celsius in 100 milliliters of water. Now, this graph, if you look, this is for 100 milliliters of water. So if you see that in 100 milliliters of water, you can kind of just ignore that because all this information is referring to a sample of 100 milliliters of water. So really, how much potassium nitrate will dissolve at 60 degrees? So first, let's find the line for potassium nitrate. That's right here. Okay. And then we want to know 60 degrees. So you go find 60 degrees, go up to that line, turn, and come follow it over here to find your amount, which is going to be about 115 grams of potassium nitrate. All right, then the second question here, okay, very similar to the first. The first one said, how much potassium nitrate will dissolve at 60 degrees? And we said that was 115 grams of potassium nitrate. The second question says, all right, we're still at 60 degrees. How much potassium nitrate will dissolve at 60 degrees? But this time it's in 200 milliliters of water instead of 100. Now, since this graph is only for samples with 100 milliliters of water. If we have a sample of 200, we have to double anything we find on here because if we have twice as much water, that means we can dissolve twice as much of whatever this graph says. So the graph told us that at 60 degrees, 115 grams will dissolve in 100 grams. If we double that, 200 milliliters of water instead, we should be able to double the amount of potassium nitrate as well. So 115 times 2 is about 230. So we'd be able to get about 230 grams of potassium nitrate into that 200 milliliter sample. Okay. Now, you can also get a question that's asked the other way, opposite from this first one. It says, at what temperature can you dissolve 220 grams of potassium iodide in 100 milliliters of water? So again, it says 100 mils, so we don't have to worry about that number at all. The only time you worry about that is if it's something besides 100. So, at what temperature can you dissolve 220 grams of potassium iodide? So first find your potassium iodide line, that's this one here. And this time, they're giving us the amount that we dissolve, and we're going to try to find the temperature. So we find over here where it says 220 grams, which is right here. Follow that line until you hit your potassium iodide line. Make a turn. Whoops. Make a turn. So we go here, make a turn, come down. Looks like it's about halfway between 45 and 60. So I don't know, 52, 53 degrees would probably be an acceptable answer. Okay, so sometimes they'll give you the temperature and you find the amount. Sometimes they'll give you the amount and you find the temperature. Okay, one just general thing that we should notice, and we talked a little bit about already, is that as the temperature increases, solubility increases. So you see all of these lines seem to be going uphill. Some of them go up a little steeper than others, but as you get a higher temperature, all of the solubility is increasing. So you're able to dissolve more solids as you increase temperature. For gases, same idea when you're reading them. So how much oxygen will dissolve at 40 degrees Celsius? You have 40 degrees Celsius, you find that oxygen line, take a turn, it's going to be about 1 millimeter of oxygen. Okay. At what temperature can you dissolve 1 millimole of carbon monoxide in water? Carbon monoxide is CO. So if you have 1 here, you find the line, you take a turn, you come down, it's going to be about somewhere around 22 to 25 degrees. Sometimes it's hard to estimate between the lines. Okay. Now notice the trend for gases is a little bit different. As you warm up, because you can dissolve a gas into a liquid as well. We have that with soda, right? You have carbon dioxide dissolved into the liquid. As you warm up the liquid, in this case, the gases are less soluble. I always remember that because warm pop goes flat faster. So as that pop warms up, it cannot hold on to its the gases that have been dissolved in there as well. So that always helps me remember that the trend is downhill. Remember, for solids, they all went uphill. As you warmed them up, you could dissolve more. Well, as you warm them up here, you can dissolve less if it's a gas. Okay? You have this solubility chart in your notes, and you're going to use this solubility chart to answer all the questions on your solubility curve worksheet, which does not go in your notebook and should be turned in when it is complete. As you're working through this, anytime that you get stuck, make sure you're asking for help right away. Don't spin your wheels too long so we can keep you moving. All right?